Okay. So I'd like to welcome everyone to this inaugural set of ChemHISTTalks. The History Division is bringing you two talks that were at the New Orleans meeting this spring. The first speaker is Dan Rabinovich. Dan was born and raised in Lima, Peru, where he developed a keen interest in stamp collecting at an early age, and he later obtained his BS degree in chemistry from the Catholic University. After he got his PhD in inorganic chemistry from Columbia University with Jed Parkin in 1994, and doing some postdoctoral work at Los Alamos National Lab, he joined the Department of Chemistry at UNC Charlotte, where he stayed for 25 years. And then in July of 21, he moved to the Joint School of Nanoscience and Nanoengineering in Greensboro, North Carolina, where he assumed the position of Associate Dean and continues working on synthetic and structural inorganic, bioinorganic, and organometallic chemistry. The title of Dan's talk is Stamps Are Planar, Carbon is Not, a Philatelic History of Stereochemistry. Dan, take it away. There we go.
Okay. Welcome, everyone. I would like to start by thanking Vera for the kind introduction, to Anna for hosting this webinar, and of course for the ACS Division of the History of Chemistry for inviting me to make this presentation. This talk is a slightly updated version of the one I presented in New Orleans a couple of months ago for the third dimension in chemistry symposium, as I mentioned here. Okay, so we'll start with just a quick definition of stereochemistry, the study of the relative spatial arrangement of atoms that form the structure of molecules. Stereoisomers, right, that's a key word today, have the same molecular formula and atom connectivity, but differ in the geometric positioning of the atoms in space. So it's all about three-dimensional chemistry. And so this slide shows kind of a busy slide, but it shows a timeline of the history of stereochemistry. I should mention that today I will cover most of these timelines, most of these milestones, but very often I am limited by what I could illustrate with postage stamps, because that's kind of what I do, applications of chemical philately. And so some of the key milestones will be covered today, and maybe I will include a few that are not on this timeline, but we'll see how that goes. Typically, these timelines start with Francois Arago, French physicist, astronomer, and mathematician, who in 1811 was the first one to describe optical rotation. He observed that quartz crystals rotated the plane of plane polarized, or as we call it today, circularly polarized light. And so there's a couple of stamps here, France and Moldova, that show Francois Arago. And so that's the paper from 1811, Memoir on a Remarkable Modification that Light Rays Experience During Their Passage Through Certain Translucent Substances and on Some Other New Optical Phenomena. Pretty cool, 1811, that's maybe when the story starts. He also worked on electromagnetism. That was with the French physicist and mathematician André-Marie Ampère, which is maybe better known. And as a matter of fact, both Arago and Ampère appear on a postage stamp from France, both of them together. Ampère, I would argue, is better known than Arago, and so it's not surprising that he has appeared on several stamps from other countries. Next milestone, I would say, is Jean-Baptiste Biot, French physicist, mathematician, astronomer, who found in 1815, 4 years later, that some non-crystalline substances, so liquids, gases, solutions, also rotated polarized light, not just solids, not just crystals of quartz. And the publication was in 1815 in this bulletin of the Philomatic Society of Paris. And I had to look that up. Philomatic is a very cool word. It means an association of individuals or of people who are interested in science, which is basically all of us. So I thought that's a very cool word to bring back to life. Anyway, and but biot does not appear on any postage stamps, but a mineral or a subgroup of minerals named after biot do appear on a stamp that I show here. It's a complicated aluminosilicate, but that's biotite, and it's named after biot. Louis Pasteur, next important milestone, French chemist, microbiologist, one of the scientists that has appeared the most on postage stamps. I think there's like 100, 110 different stamps with Louis Pasteur. Here I show a few, including some from countries that have no connection to Pasteur, like Taiwan, Cuba, or Gabon. But anyway, that's Louis Pasteur. Louis Pasteur was born in the small town of Dole, in the Franche-Comté region in eastern France, 1822, so there's a stamp to show that. He received his BS degree in 1845 from the École Normale Supérieure in Paris. That's a stamp from the ENS in Paris. And then 2 years later, he received his doctorate, his PhD from the University of Paris. So pretty young. So if you look here, Pasteur was born in 1822. At the age of 25, 26, he came up with the discovery of molecular chirality. That's very young age, pretty incredible. He had 2 theses, chemistry and physics, was appointed professor for a short period of time at the Lycée in Dijon, then moved to Strasbourg. In Strasbourg is where he conducted those famous experiments with sodium ammonium salts of paratartaric acid being a racemic mixture of tartaric acid. And that's when he separated those crystals by hand, a very tedious piece of work, but he was able to separate and then analyze the optical rotation of these enantiomers, as we can call them today. And the crystals of paratartaric acid appear on this French stamp, 1995. Of course, you've maybe seen these images before. Same thing in the first day cover for this stamp, the postmark, this cancellation shows those crystals. And also in this relatively rare stamp from the territory of Afars and Isas, but the crystals are there. So this is not Louis Pasteur with images of, dogs or the rabies vaccine. There's many of those, but Louis Pasteur as a chemist with these crystals. And where is Afars and Isas anyway? And so I show this because I think it's pretty cool. The French Somaliland was a French colony in Africa, in the Horn of Africa for a long time. It became the French territory of Afars and Isas for about a decade before the country gained independence, and it's now Djibouti since 1977. It's a small country here between the Red Sea and the Gulf of Aden. And so it's right there. Djibouti is that country. Anyway, and the key report, right? May 22nd, 1848, Louis Pasteur presents the results of his experiments to the Académie des Sciences in Paris. This was a relatively short communication and memoir on the relation that may exist between crystal form and chemical composition and on the cause of rotatory polarization. So this is a very important paper that was published, again, 1848. And the full paper was published a few months later in the Annales de Chimie et de Physique. And a very detailed analysis of these 2 papers was conducted by a good friend of the history division, and which appear in the Bulletin of the History of Chemistry, detailed analysis of these two papers, and he concluded that the first one, the communication, the shorter paper, was really the one that merited the citation for a chemical breakthrough award, which is given by the Division of the History of Chemistry. And so very important paper. Then Pasteur continued working on crystals and molecular chirality for about 8 years, and his discoveries included the thermal interconversion of enantiomers, what we call now racemization. So that was part of that. In 1854, he was appointed professor of chemistry and dean of the new Faculty of Sciences at the University of Lille. He, as you can see, moved several times during his career. It was during his inauguration speech at Lille that he said that in the field of observation, chance favors only the prepared mind. Famous words, but that's when he said that. And in 1856, still at Lille, he stopped working on molecular chirality and all of a sudden began investigating fermentation processes. He discovered in subsequent years the role of microorganisms in the spoiling of wine, beer, and milk, invented, of course, pasteurization around 1864. And well, the rest is history. In 1877, he studied also infectious diseases, developed vaccines, not only for rabies, but also for chicken cholera, for anthrax, and there's lots and lots of stamps that show part of that work he did after his work as a chemist. In 1887, he also founded the Pasteur Institute, which is now has 33 branches all over the world, and it's a big and important nonprofit biomedical research institution. And so that's still part of his legacy today. The Dutch, now we come to 1874. 1874, of course, was the 150th anniversary that led to the symposium in New Orleans a couple of months ago. And so that is the tetrahedral carbon. The Dutch physical chemist Van Hoff and the French chemist Joseph Achille Lebel, working independently and almost simultaneously, proposed in 1874 that it was the tetrahedral geometry of carbon that explained the optical activity of these carbon-centered compounds bearing 4 different substituents. And so it's very remarkable. It's a case of maybe simultaneous discovery. Their papers were published 2 months apart. The first one was Van Hoff. He published this 12-page booklet or pamphlet, as it is always referred to, and was sort of self-published, relatively low distribution, September of 1874, whereas Lebel's paper was in the Bulletin of the French Chemical Society. So that had a lot more distribution. But in a few months, Van Hoff translated to French and expanded this original paper, and that became a 45-page paper that he published as a small book subsequently next year, 1875. And so reception of Van Hoff's 1874 paper, it was in general pretty enthusiastic. One of the maybe most visible advocates was the German chemist Johannes Wislenus, who had studied for several years the problem of excess enantiomers, excess isomers in lactic acid. And this is a Dutch stamp that shows his cardboard models for the tetrahedral carbon and the structural diagram of lactic acid. This early work is described in this very cool paper in the Journal of Chemical Education. And so that was with Licenus. But there were some people who were a lot more critical of Van Hoff's paper, and that includes the German chemist Hermann Kolbe, who was merciless. A couple of years later, in 1877, he published a critique of his full paper, the book, the small book published as La Chimie dans l'espace. And he says that Van Hoff appears to have no taste for exact chemical research. It is not possible, even cursorily, to criticize this paper since its fanciful nonsense carefully avoids any basis of fact and is quite unintelligible to the calm investigator. Like, wow. And that was tough criticism from a well-known chemist, but of course, Van Hoff had the last word a few years later. Colby, by 1885, Colby was dead. He passed away in 1854. And then Wislicenus became the chair of chemistry at the University of Leipzig. I think this is a typo, it should be 1855. Okay, so Van Hoff, of course, moved away from organic chemistry within the next 5 years and embarked on a distinguished career studying chemical kinetics and thermodynamics, physical chemistry. That is maybe even better known for Van Hoff, several stamps with Van Hoff. And of course, he was the first recipient of the Nobel Prize in Chemistry in 1901. And these are stamps that show Van Hoff, also Röntgen, who got the first Nobel Prize in physics and so forth. And this is an interesting souvenir sheet with 6 stamps that was issued in Mozambique for the 160th anniversary of the birth of Van Hoff. So there's Van Hoff here on this central stamp, Rutherford, Ostwald, Ramsey, Curie, all kind of contemporaries of Van Hoff. I have no idea why they decided to include Negishi, right? Palladium catalyzed coupling reactions, got the Nobel Prize in 2010, which has nothing to do with Van Hoff of his work, but there you have it. Anyway, Fischer projections, next milestone, 1891. The German chemist Emil Fischer studied very, very important contributions, studied esterification reactions, the synthesis of sugars, developed a way to draw organic molecules with chiral centers. That's important here, Fischer projections as we know them. And he also proposed a lock and key mechanism for enzymatic reactions, very important contributions. So that's Fischer, a couple of stamps for Fischer. And he received the second Nobel Prize in Chemistry in 1902 in recognition of his work with the synthesis of sugar and purines. And this is the paper from 1895 that show the very first Fischer projections, which is pretty cool for different sugar molecules. And then fast forward a few years, and we come to William Thomson. William Thomson, known as Lord Kelvin, was a man of many talents, British mathematician, physicist, engineer, best known for his work on the first and second laws of thermodynamics, transatlantic telegraphy, and of course the absolute temperature scale. It's a couple of stamps that show him. He was born in Belfast, but most of his work was done at the University of Glasgow in Scotland. Anyway, why Lord Kelvin? That's the paper in 1848 with the temperature scale. But it was in 1893 that among his many contributions, he came up with a definition of chirality, and he introduced that term. On May 16th, 1893, Lord Kelvin presented the second Robert Boyle lecture to the university, to Oxford University, the Junior Scientific Club. And he said, I call any geometrical figure or group of points chiral and say that it has chirality if its image in a plane mirror, ideally realized, cannot be brought to coincide with itself, right? Non-superimposable images. This was published the next year in a small book with a very interesting title, The Molecular Tactics of a Crystal, and that's Lord Kelvin of Kelvin temperature. And so that's a nice contribution, maybe a lesser known contribution for Lord Kelvin. Paul Walden was a Latvian chemist, an organic chemist, known for his work in stereochemistry and the electrical conductivity of molten salts. He coined the term solvation. He also came up with the first room temperature ionic liquid, which has nothing to do with stereochemistry, but I think it's a cool cool little fact. And of course, he's maybe well known in the context of stereochemistry for the Walden inversion. This was proposed in 1896, and it's related to the inversion of a stereogenic center in a chiral molecule in a chemical reaction, right? So that tetrahedral carbon that is inverted during an SN2 reaction, and we've all studied these trigonal bipyramidal intermediates and so forth. And so that's a small souvenir sheet from Latvia that shows Paul Walden. And Alfred Werner, I had to mention Werner because I'm an inorganic chemist, of course, the father of coordination chemistry, 1913 Nobel Prize in Chemistry, in recognition for his work on the linkage of atoms in molecules, and you can read that in there. Lots and lots of work with isomers, typically with octahedral cobalt compounds. He appears on a stamp with Kamerlingh Ons, who received the Physics Prize the same year, 1913, for the production of liquid helium and the study of superconductivity. But that's Werner. Werner does appear on a couple more stamps, but again, most relevant to this talk is that he was the first to describe optically active coordination complexes in 1899. He established the molecular asymmetry of coordination complexes that typically contain chelating or these bidentate ligands like ethylene diamine that is shown here. And so that demonstrated that the chirality, optical activity, was not restricted to organic molecules or that carbon-centered molecules, which is, again, expanding the field of stereochemistry. The structure of camphor was established in 1893, and I'll tell you why I like to show camphor. That's the molecule of camphor. The one on the left is the one that is naturally occurring. The structure was, many different wrong structures were proposed until 1893, when Julius Bredd, a German organic chemist, proposed that the correct structure. Julius Bredd may be better known to some of you as the Bredd's rule. A double bond cannot be placed at the bridgehead position of a bridge ring system. Interestingly, he also invented a piece of glassware that is called officially the Bredd distributor. It's commercially available as I think as a distribution adapter. It's used for fractional distillations. I've used it many times in my lab. We just call it a cow. So that's kind of our common name for that. Anyway, so that's camphor, Bredd. And camphor is important because it was the first molecule to be to undergo a total synthesis. The total synthesis of camphor was completed in 1903. And it's, of course, the total synthesis because what Compa, a Finnish chemist, did in 1903 was the synthesis of camphoric acid, but it was earlier, around 1900, that camphor had previously been obtained from camphoric acid. So all Compa had to do was develop the synthesis of camphoric acid, and basically the assumption is that the synthesis was complete. And I like camphor because it appears on this very cool stamp from Finland, 1991, because it's a stereoscopic stamp pair. If you look closely at the two stamps, there are small differences between them, and you see the three-dimensional representation of the stamp. 1991 was the centennial of the Chemical Society of Finland, and Ashan is another Finnish chemist that appears on the first day cover. Fluorite has also appeared on a pair of stereoscopic stamps that I show here. And then I'm going to jump to conformational analysis. So 1950, the study of different energy levels associated with different conformations of a molecule. I write 1950 because that was Barton's seminal paper in Experiencia published. The conformation of the steroid nucleus. There was lots of preliminary work done by Barton and others on the conformations of, say, cyclohexane and so forth. But I'll fast forward to that part of the story. And so he shared the 1969 Nobel Prize in Chemistry with a Norwegian physical chemist, Odd Hassel. He's the one that really studied extensively the different conformations of cyclohexane, mainly using gas phase electron diffraction. But they shared the Nobel Prize in Chemistry in 1969, really the fathers of conformational analysis. The stamp that I show here with this steroid is part of a set of 4 stamps, beautiful stamps issued in the UK in 1977, and the one for Barton and conformation analysis in the upper right corner is the one that is really nice. And I have in my collection a first day cover that is signed by both Barton and Richard Singe, who got the Nobel Prize in Chemistry in 1952 with Archer Martin for their invention of partition chromatography. So a nice souvenir with 2 different signatures of Nobel laureates. 1965, so we are in the hot area in the 1960s for stereochemistry, Woodward-Hoffman rules, well known for these 5 papers published in 1965 that describe the outcome, activation, energy, and stereochemistry of pericyclic organic reactions. 1965, of course, is the year when Woodward got the Nobel Prize in Chemistry. He would have shared the Nobel Prize in Chemistry in 1981 with Kenichi Fukui and Rolf Hoffman, but he passed away in 1979. So he couldn't share that second Nobel Prize, which he surely would have received. Anyway, stamp-wise, I think there are a few stamps with Fukui. Hoffman, Woodward and Hoffman have not been as lucky with stamps. And so the first one was in 2004, a weird stamp that shows a kind of youngish Rolf Hoffman with a locomotive, which is kind of crazy. A much better stamp was issued in 2017 in Ukraine, which the design was consulted with Rolf Hoffman, and that shows the molecular orbitals of butadiene, and it's a much nicer stamp. As for Woodward, he also has a weird one and a good one. The weird one is from the Republic of Guinea, which shows him with a gorilla for reasons that it's just very weird. And a better one shows the structure, the molecular structure of reserpine. He completed the total synthesis of reserpine in 1956. And Kahn-Ingold Prelog priority rules, 1966. We study this all the time, R and S, E and Z, alkenes. All of that was in 1966. 1966 is the year of their very well-known publication in Angewandte Chemie. Of these 3, Prelog is the only one that has been honored on a postage stamp. Of course, he shared a Nobel Prize in chemistry in 1975 with John Cornforth. For Prelog was for his research into the stereochemistry of organic molecules and reactions. So there's a couple of stamps with Prelog there. And I show one more with adamantane, because the connection to adamantane is that Prelog was the first one to synthesize adamantane in very low yield, but he synthesized adamantane in 1941. Okay, and last, we're almost coming to an end. Asymmetric catalysis started really in 1968 by Knowles and Noyori, mainly doing hydrogenation reactions. And they shared the Nobel Prize in Chemistry in 2001 with Barry Sharpless, who did mostly oxidation reactions. And again, the use of chiral auxiliaries and asymmetric catalysis, which is huge, right, in the pharmaceutical industry and organic chemistry. And so philatelically speaking, no stamps for Knowles or Noyori, Sharpless a little bit. Monsanto, I show this because Knowles did most of his career in industry at Monsanto. Sharpless does appear on a more recent stamp from Guinea-Bissau for his second Nobel Prize in Chemistry, 2022, and this is a pretty nice stamp which also includes Caroline Bertozzi. So that's for the 2022 Nobel Prize in Chemistry. Last but not least, I asked the question, is tetracoordinate carbon always planar? The answer is probably not. In 1968, Monkhorst was the first to suggest a planar tetracoordinate carbon intermediate in the interconversion of substituted methanes. It's a paper in 1968, and you can see here this planar intermediate. After that, several researchers, including Rolf Hoffmann, but several others have subsequently studied computationally and sometimes even isolated real examples of compounds containing planar tetracoordinate, four-coordinate carbon centers. I should point out that the ones that have been isolated and even crystal structures obtained typically are organometallic compounds, so they contain at least one carbon-metal bond. But carbon could be planar. Four-coordinate carbon could be planar. And so I have to just thank again the organizers of the Birth of the Third Dimension in Chemistry Symposium in New Orleans, Art Greenberg from the University of New Hampshire, David Lewis from the University of Wisconsin-Eau Claire, the Division of the History of Chemistry for this opportunity to present to all of you. And thank you very much for your attendance.
Thank you, Dan. That was a great talk. We have some comments in the chat. Let me get it back to that. Okay, so Carmen Junta noted, not a question, just a comment, that Werner had women students in his lab. Edith Humphrey prepared some of the complexes later discovered to be a racemic mixture. More details in the upcoming spring issue of the Bulletin for the History of Chemistry. And next was from Pedro Cintas. Dan, what a wonderful talk, merging history and stereochemistry. Just a curiosity, a large portion of stamps on stereochemistry have been released by non-European countries. Why? If you give some thoughts to this. Thanks again.
Yeah, some of the stamps, the market is very, very particular. I mean, some stamps, the stamps honoring Woodward and Hoffman, except for the one from Ukraine, are from completely random countries. Those are stamps that are often tailored to stamp collectors, I would say, valid for postage, but really issued for the, the philatelic market. And why so many stamps with stereochemical topics are in non-European countries? Well, they can be from anywhere in the world, but that's just the way things are. If you think about it, there's no, I don't think I've shown a single stamp from the US in this presentation. That's just the way it is.
Another question from Jingbo Louis. Which country has the most science-themed stamps, and what must one do to get onto a stamp?
Yeah, so in terms of countries that have the most stamps related to science or chemistry in particular, I would say it's probably Russia, just because they have lots and lots of stamps issued. And they have a lot of history with the chemical industry or science. Other countries, Germany, France, have many. And how to get the stamps? Most of these images can be found online. Now, I tend to get my own stamps to have my own high-resolution images. But where do I get the stamps? It's online, eBay, stamp shows. Nothing really is particularly expensive in my collection of chemistry-related stamps. So it's just takes a long time. But anybody interested in any images from today's presentation, just send me an email and I'll share any images you want. I have them all.
Okay. Well, thank you, Dan. We'll go to our next speaker. Okay, so our next speaker is Peter Villarreal. Pete is from Kingsville, Texas, where he received his bachelor's in chemistry from Texas A&M Kingsville. He's currently working on his master's degree with his advisors, Sajid Bui and Jingbo Louis, and he hopes to finish in this August. His research centers the use of metal organic frameworks, or MOFs, and nanometals, and specifically on the use of MOFs as bactericidal agents. His interest in the history of chemistry started in 2017 when he was an undergraduate, and attended a club on campus called the Periodic Table Club, which was hosted by Dr. Christine Hahn, and they discussed the history of various elements. He hopes to obtain a PhD degree and teach inorganic chemistry. He's a member of our division, the history of chemistry, as well as energy and fuels and colloid and surface chemistry. Pete gave his talk in the History of Catalysis Symposium at the spring meeting in New Orleans, and I welcome Pete. Take it away.
Hello, everybody. Thank you for having me. Let me just share my screen. Okay. At any point, if you can't hear me or you can't see what I'm doing, please let me know so I can adjust on my end. As she was kind enough to mention, I'm from Texas A&M University, Kingsville, and I will be giving my talk today on Carl Ziegler and Giulio Natta and their impact on modern catalysis. And mainly I'll be focusing on their development of the Ziegler-Natta catalyst, which I'm sure everyone is very familiar with. So I'll start off with some background about the scientists themselves. So to begin, Carl Ziegler was born in 1898. He is a German chemist, and he was born, his father shared the same name as him, and his mother was named Louis Ziegler. It's interesting because compared to some other scientists, Carl Ziegler and Giulio Natta don't have a whole lot of information dedicated to them about their early childhood and teenage years. A lot of scientists have very well documented upbringings, mainly who they learned from or how they learned or what drove them to pursue science. But Carl Ziegler really more anecdotal than anything else. And so the early part of his story is that he received a physics book, and it was his love of that physics book that pushed his desire to want to continue studying science and chemistry in general. But beyond that, there's not really a whole lot that I was able to discover about what motivated him to become a scientist. He did attend the University of Marburg, and he began his PhD studies in the mid to late 1910s. Unfortunately for Carl Ziegler, and we'll see this again in a little bit when I talk about Giulio Natta, they were scientists at a point in time where politics and history was sort of the antagonist to growth and science. They were both scientists during both World Wars. And so his PhD studies were actually interrupted in 1918 because he was required to participate in World War I for the German army. Luckily, that interruption did not last long, and in 1920, he was able to receive his PhD under von Auers. And if you're familiar with von Auers, he is also the advisor to Wittig as well. So this is a particularly strong chemistry family that we have here is von Auers and Ziegler and Wittig, and Ziegler and Wittig both very well known in organic chemistry. So Carl Ziegler had a magnificently decorated life as a scientist. And so I could fill up an entire slide with just the awards and medals that he received, and I just wanted to highlight a few of them. So in 1935, he received the Liebig Medal. In 1940, he received the War Merit Cross. He was a recipient of the Lavoisier Medal, the von Siemens Ring in 1961, and then, of course, the Nobel Prize in 1963 for chemistry, which he shared with Giulio Natta. One of the awards that I want to point out, aside from the Nobel Prize, which he's most famous for, is this War Merit Cross that he received in 1940. This was just one of many awards that he received that after the end of World War II had to be re-given to him without affiliation to the Nazi party, to not diminish his contributions to science, so that his contributions to science were not directly linked with the governing body that gave it to him at the time. So that was just one of the many awards that was reissued to him by the German government once the Nazi regime fell in 1945. In 1922, he married Maria Kurtz, and both of his children, Erhard Ziegler and Mariana Ziegler, went on to become doctors themselves. Part of that sort of antagonism that he had toward the Nazi party, it was a sort of silent protest. He was not really able to verbally and vocally and loudly display his disagreement with the Nazi regime at the time. Although I will talk about a significant moment in his life a little bit later on involving the Nazi regime. But part of what he did to protest in silence was to show that he had a deep love for the humanities and for the arts. And so even upon his passing, a large portion of the private collection of the art that he had collected with his wife were donated to support the Mulheim-Ziegler Art Museum. And it just sort of emphasizes the care for humanity that he had beyond what may have been attributed to him in the late 1930s and early 1940s. Even beyond that, financially, he donated from his own money from patents that he had made over 40 million marks to support the research at the Max Planck Institute. And Carl Ziegler passed away in 1973. It's possible that there are people who met him or know him. I don't, but that's fine. I want to show this here. This is a plaque that is dedicated to his memory in Germany. And this picture that is on the left, it really shows him, you know, as the human that he was. This is Carl Ziegler dancing with his granddaughter at the Nobel Award ceremony when he received his prize in 1963. A little bit of background on Giulio Natta. So Giulio Natta was Italian and he was born in Imperia, Italy. And he attended and graduated the Politecnico di Milano school as a chemical engineer in 1924. He was a very well-renowned teacher, and he was considered not only to be a very gifted engineer and gifted scientist, but also a very gifted educator who cared very deeply for preparing the next generation of students with information. And he taught at many institutions. So he taught at the Politecnico di Milano, the University of Milan, Pavia University, the University of Rome, and the Polytechnic Institute of Turin. Very similar to Carl Ziegler, his life was marred by the politics of the time. And so in 1938, he was appointed the head of the chemical engineering department at the Politecnico di Milano. But this happened entirely because of the forced removal of Mario Giacomo Levi, who was forced to step down because of the fascist government that was in Italy at the time. So Levi was removed from his position and Natta was appointed to take his place. This is one of the many, you know, points of history where we don't know how things may have turned out if that had never happened, and it was a horrible and unfortunate situation of history. But it did prepare the rest of what I'm going to discuss to be able to happen, is that Natta was able to take on this position. In 1935, he married Rosita Beati, and she was a very well-known lover of literature and languages. And even though he was the scientist of the pair, it is actually she who coined the very famous and still used terms to this day, isotactic, atactic, and syndiotactic, to refer to the arrangement of methyl groups on polymers. She took those terms or those prefixes from general words that she knew, and she gave them to Natta, and he used them in his publications. The two of them also had two children. And eventually Natta passed away at the age of 76 from Parkinson's disease. Here's a photo of him and his wife. I did mention when I gave this talk in New Orleans that there are not so many photos of Giulio Natta, especially later on in life. And there are not really any photos of him that I was able to find receiving his Nobel Prize. And as it was pointed out by someone at the previous conference, and as it makes sense, for someone who is, you know, has Parkinson's and he was carried onto the stage by 4 of his colleagues and his son, it may not be a time that he may have been particularly fond of having photographed. And I don't know if there are any photographs of that moment, but that's something that, you know, I would like to see. It's a part of scientific history that is not shared very well. So going into the discovery of the Ziegler-Natta catalyst, or going into their pursuit of it. So all of this sort of started on Ziegler's end with his work on what he called the studies on trivalent carbon. So there's a series of 24 papers that involve tetrahedral radicals and organoalkali chemistry. And he worked with Kurt Barr, and he attempted to react 2 phenyl isopropyl potassium to form stilbene. They were intending to prepare dipotassium diphenylethane, but they instead noticed an addition reaction instead. And when he gave his talk to receive his Nobel Prize, Ziegler did say that this was the first example of the addition of an organometallic compound to a carbon-carbon double bond a reaction that was hitherto completely unknown. This reaction was clearly a general one with a wide range of applicability. So this is sort of the start of Ziegler's curiosity into something beyond what he was originally looking to attempt to do. And so this led into him wanting to synthesize 1,2-polybutadiene. And so he moved his work into lithium alkyl compounds. And so at the time, he was a little hesitant. These compounds were a little difficult for him to prepare, and they used mercury salts to prepare the material. We all know the dangers of mercury now, so it's a good thing that he moved away from this type of chemistry while he had the chance. And he developed his own process. So he moved on to develop a process of treating T-butyl chloride with lithium metal at 35 degrees Celsius. And the problem that he discovered, which is going to be a very important problem later on, had to do with the distillation of butyl lithium. It was sort of unstable at certain temperatures. And this is very important to the work that he later discovered. And so what he wanted to do is he wanted to use a good trapping reagent to achieve his goal. And so he began his work with triphenylmethane, but this proved to be very slow for the reaction kinetics. So he eventually replaced this with dicyclohexylamine. And I want to point out, though, it is something that I don't have a slide for, but it is very important that this isn't the first attempt that a scientist is making at producing this polybutadiene. So in around 1910, Lebedev, who was a Russian chemist, had already worked to synthesize butadiene itself. And he had already worked to use sodium by the 1930s to form polybutadiene as well. So I do want to point out that this is, innovation is often accompanied by challengers and by other people that are equally interested in trying to do what you're doing as well. And this is something that he definitely saw, and he had other competitors that I'll discuss in a moment. So one thing that Ziegler did say about his work was that our results produce no evidence at all for the formation of radical intermediates in the course of the alkali metal polymerization. On the contrary, all the evidence obtained to date speaks for these processes being entirely due to organometallic syntheses. So this is sort of the first time that he's realizing that maybe what he was originally thinking was going on wasn't quite, correct, that there's something else going on here that he can investigate and work with to try and figure out what is the mechanism for the chemistry at hand that he is observing. And so a big push forward for him was being promoted in 1936 to be chair at the University of Halle. And so, as everybody knows, this is not a secret that, is hidden to us today. With more funding and resources, you have a better chance of figuring it out what you're looking for. And that is exactly what was made available to Ziegler in 1936, was more funding and resources. And so because of this, he was able to make advancements that he hadn't made before. And so he was particularly curious at developing a difference between 1,2-polybutadiene and 1,4-polybutadiene. And what he discovered was a very significant temperature difference. So he was able to form 1,2-polybutadiene at -70 degrees Celsius and 1,4-polybutadiene at 150 degrees Celsius. And so he was quoted, when he gave his speech, he said, of all the factors, namely temperature, rate of addition of butadiene, the solvent chosen, and the type of alkali metal, the temperature alone determines the constitution of the polymer formed. And so that was a very important discovery for him with what it was that he was trying to do. We know now, and we'll see in a little bit, that the catalyst has a significant development in how we're able to develop the polybutadiene. But just for the sake of developing the polybutadiene, this is what he determined was the significant factor. And so this all comes into him eventually using ethyl lithium as a compound. So in the late 1930s, he was approached by the Nazi regime and asked if he wanted to become the head at the Kaiser Wilhelm Institute for Kohlenforschung. I know I'm not saying that correctly, to replace Franz Fischer. And it was an interesting move on Ziegler's part, because essentially what happened is that Ziegler approached the Nazi government and told them that he would make the move, but that he would be in charge of the research he was going to do. And this, you can see why this could have gone wrong very quickly, to challenge the Nazi regime and tell them that they were not going to be in charge of what he was going to research, that he wanted to be in charge of what he was going to research. I don't know if it is the potential application of the use of this in the rubber industry, that the Nazis acquiesced and were okay with him doing what he was going to do. But the important thing is that there was relatively little pushback from the Nazi regime, and they allowed him to have control over his own research when he moved over to this institute. And so because of that, it was here that he noticed something very odd while he was using butyllithium in his reaction. So he noticed that it was decomposing and producing lithium hydride. So he switched over to ethyl lithium, which was sort of dealing with the same problem. But the curious part is that while he was doing this, he was forming butene in the final product of his reaction. And here's a photograph of the institute that Ziegler eventually moved on and did this research at. So here's the problem. Here's what he deduced, like, a good scientist might. So he came to the conclusion that ethylene has 2 carbons in it and butene has 4. So he came to the determination that it was dimerizing during his reaction. And so he believed that ethyl lithium was undergoing an addition reaction with ethylene, and that this should be a reversible reaction. And this is the reversible reaction that he came out to, where he has ethyl lithium breaking down and forming this ethene and lithium hydride. The problem, though, is because lithium hydride is insoluble, he had very high difficulty trying to prove the reverse reaction. So he's only able to show the forward reaction and not the reverse reaction. And so he believed that this was a dead end to his work. But in 1949, Gellert, who was working with Ziegler at the time, decided to use a compound, lithium aluminum hydride, which had recently been developed by Schlesinger. And when he used this, he was able to see that he formed a mixture of terminal alkenes and what we now call, or what is called an Aufbau reaction. So for the first time, Ziegler is able to generate molecules of an incredibly significantly high molecular weight that he hadn't been able to do before. And so for him, triethyl aluminum became the catalyst of choice, although he did have some difficulty preparing the compounds, especially at the industrial scale. And this is where Giulio Natta comes into the equation and unites him with Ziegler. So in the early 1950s, Ziegler gave a lecture about his discoveries. And as fate would have it, or however you want to look at it, Giulio Natta was in attendance at this talk. And at the time, Natta worked for an Italian chemicals company called Montecatini. And when he saw this talk, he invited Ziegler to go and speak in Milan. And Ziegler accepted. And it was then that Montecatini was given license to apply Ziegler's work. And I do want to point out, though, that similar licenses were also given in England to petrochemicals and in the United States to the Hercules Powder Company. And here's actually a photograph of Ziegler at the Hercules Powder Company. I also want to mention, though, very similar earlier how I mentioned Lebedev doing similar work on the development of polybutadiene, that at the time in America, the Phillips Chemical Company was also developing a catalyst to do this very similar type of work. And they used a chromium catalyst that we call a Phillips catalyst, which is still a very important catalyst to this day for the formation of polybutadiene. It's the same thing that I mentioned earlier, right? So innovation requires competition. And so there is this competing American group that is forming this at Phillips at the same time that Ziegler and Natta are beginning to work together in the early 1950s. It was also in the early 1950s that they hit a breakthrough, though, that was significant to the development of the compounds they were trying to make. So by 1953, it was already well established that Ziegler's method worked in the formation of this polybutadiene. But Holzkamp, who was working with Ziegler, ran into problems while he was trying to do his doctoral work. And very similar to what Ziegler was going through in the beginning, he was only able to form butene from the ethylene. And so I didn't really write it in my presentation, but the history of it, the anecdotes of it say that Ziegler was not very nice about it when he was approached by Holzkamp, and in a very colorful way told him that he messed up when he was preparing the triethyl aluminum batch in the beginning. And Holzkamp luckily was able to determine, though, that it wasn't him that was really at fault. The true culprit was nickel that had been left behind as an impurity in the autoclaves when they had been improperly cleaned. And this was an important turning point for Ziegler and Natta. And Ziegler had an idea, which that if nickel could do this, maybe other metals could do it. And they wanted to scour the periodic table to figure out which metals could facilitate this reaction better And luckily for them, the metal that they came to was titanium, which is very early on in the transition metal group. So they didn't have to do quite nearly as much work as they thought they were going to have to. So in 1953, Braille discovered that zirconium acetylacetonate was able to produce polyethylene under relatively mild conditions. But he would eventually test titanium tetrachloride, and he discovered that titanium was even more effective than zirconium at what it was that they were trying to do. And similar to this, around the same time, using Ziegler's work, so remember, because of the licensing, Nata had almost immediate access to what Ziegler was doing. Nata used the alpha trichlorotitanium and triethyl aluminium and was able to develop isotactic polypropylene. And so this compound that Nata developed was marketed in Italy as Moplen, which is what we call plastic now. And it was a fascinating campaign that I mentioned this whenever I spoke in New Orleans, that Gino Bramieri, a famous Italian comedian, came out on television and promoted the item to Italians all across the country as a life-changing discovery, which, as we all know, plastic is in fact a life-changing discovery. So in conclusion, and you can do deep dives into any of these things. I just really wanted to focus on the participation of Ziegler and Nata. But in conclusion, I want to say that both Carl Ziegler and Giulio Nata helped to advance science in a way that I don't think anybody could really comprehend what today's world would be like without their discoveries and without their contributions to science. There's certainly nobody in the current younger generation that has a concept of life without computers or technology the way that it is today. So their discoveries certainly affected our lives on a day-to-day basis. And their work led to innovations in the chemical world beyond just what they did. And so I did mention this in the last talk that I gave, and there's a big part of the dangers of plastic to our world. But I want to really emphasize that both of these men left behind a legacy of honor and achievement, and a desire to see the world improve, and a desire to see the world do better, and to change, and to make scientific and chemical progress. And I think that that's something that we should all keep in mind. And so before I finish, I just want to say thank you to the ACS in general and to the Chemical History Division for having me twice now on this topic. I really appreciate it. And if anyone has any questions, I'd be happy to answer.
Thank you, Pete. Again, job well done. I don't see any questions in the chat right now, but I will ask one, which is what got you started on this particular topic?
So I'm going to stop sharing my screen for a second. So what got me interested in this particular topic, actually, as a current graduate student in the fall, I took an advanced inorganic chemistry class with Dr. Han, who is also a member, and I believe in the group today. And one of the presentations that I gave was on the transition metal group of titanium. And that sparked my interest in learning further and going deeper into this study. And then by chance this semester, I took organometallic chemistry. So I further got to study the material in that way. But just in general, I think it was sort of just my interest in inorganic chemistry that made me curious about it.
Okay, there's a question in the chat from Jingbo Louis. What type of relationship did Nata and Ziegler have? Were they close friends or just professional friends?
I think their relationship, for the most part, that I've been able to see was mostly professional. I think that they were colleagues that held each other in very high esteem. But given the difference in their locations, maybe they were not as close. There are some stories that were shared. I believe Ziegler stayed at Nata's home, actually, at one point in time, and was able to see quite a bit of Italy that he had never seen before. So there's probably a dynamic of close friendship there, but I would say more than likely more professional than anything else.
Okay, there's a question off topic, but personal to you. Is your university the old Texas A&M? I'm not sure what that, maybe you do.
I do believe that our university was called Texas A&I before, but it was before my time. I'm not entirely sure what it was called before.
Okay, we'll go with that. Well, I want to thank both you and Dan for your talks. I think you gave great talks to bring some of the meeting to everyone who couldn't attend. For the group, the plans are to have the next ChemHIST talks after the Denver meeting. So we'll again choose, the executive committee will choose 2 talks to bring to you, and you'll get emails announcing that. This recorded talk will be posted on the HIST website within hopefully the next 48 to 72 hours. If you have trouble finding it, just let me know. And I want to thank everyone who was here today, giving support to our speakers and to the division. So thank you all very much. And I wish you a good rest of your day. Pete, or somebody, Mauro Castro says that the university was Texas A&I until 1993 and then became Texas A&M Kingsville. So now we all know something. Okay, David. And I want to thank Anna the Betancourt Diaz for arranging the Zoom call. Her help is greatly appreciated.
Thanks, everyone.
Okay, bye, everybody.
Bye.
Thanks, Anna.